go away. Here we go. Silence your phone, please. You have a question?
Yeah, for the worksheet. It's just for all the time, like to work on it?
They're just meant for you to use for practice.
Yeah. So we could just use it with the book?
Mm-hmm.
Like 1.1 and 1.2?
Yeah.
With the chapter 1?
Yeah, so like the first number in that set is which chapter it's from, and then I just number them by how many worksheets there are. They don't correlate to a section in the book. They're just different worksheets for different topics. And they're meant for, just print them out for practice, and I will bring them to, during certain lectures, I'll bring them to class and I'll work on a few problems for practice. Like I'm actually planning on bringing the first worksheet to class next week on Wednesday. So yeah, just go ahead and print all those out, and then you can work on them, talk to your classmates, work together, all that kind of stuff. All right, so today we are going to talk about the basic units of measurements and how we work with numbers here. So I am sorry, this is a really dry lecture, but we have to do this. And if you've taken a physics class before, you've already learned this stuff. We do things about the same way amongst all the different disciplines, the way we handle numbers. All right, so first things first, scientific notation. How many of you guys have learned scientific notation from a previous class? So it looks like the majority of you have. So I'm going to go quickly through this here. So the main reason why we use scientific notation is it basically gives us a really convenient way to express really large or really small numbers. Typically, if a number is not very large or very small, we don't use scientific notation typically. But you need to know how to convert any number back and forth between the two different forms. The reason why scientific notation is so useful, there's a couple reasons. One, it allows us to use the logarithmic scale. And you guys will see that kind of stuff in Chemistry 122. It basically allows a logarithmic scale even shorthands it even further. And another thing here too is that we're going to work with a metric system. And if you guys probably learned metric before, metric is all base 10. So this allows us to manipulate numbers within metric very easily. And it actually, I'm going to show you guys a few tricks today that can actually simplify a lot of different things when working with numbers in scientific notation. All right, so what's in a number? So here we have a number here, just 123.4. The main thing about scientific notation is that the number that's in front of the first number has to be a number that is greater than 1 or less than 10. And what that means is that you only have one digit in front of the decimal. Any more digits than that, you're technically not in scientific notation. So the first thing you want to do is you have to move the decimal such that it's right right after the first digit, and you want to keep track of how far you've done it. And some people like to draw little loops showing each little movement to keep mental track of how far they're moving it. The next thing you need to do is add what's called the exponential. I'm trying to use proper terminology with you guys here. Basically, you put a number 10 there. And basically, what the exponential is what you're going to be multiplying by. And since we're working in, normal number system, it's all base 10. A little side note here is I was given a math book from my wife's grandmother, and it was a math book from like 1920 or something like that. And it had like 3 chapters in there about different base number systems. And there was actually homework assignments in there where they had to do math off of base 7. It was ridiculously hard. And I thought it was incredibly difficult and to do some problems in there. And they were like 5th grade level, technically. I was like, wow, they must have been way smarter than we were now, because that stuff is crazy. And I couldn't think of the benefit of even teaching that to them, because we actually use base 10 in the world here, so why would you even bother teaching this stuff? But that's probably why it's no longer in math books. So the point is, that's why it's 10 here. All right, you then need to add an exponent to the exponential. That basically tells us how far the number moved. And when you multiply all this out, it means that this calculation is equivalent to the original number. So you're not changing the number's value in any way. You're not changing its magnitude, anything about it. You're just changing the way it's being shown. All right, and if you're moving the number to the left, that means you have a large number that's greater than 1, giving you a positive exponent. If you're moving the decimal to the right, that means you have a really small number, giving you a negative exponent. And I want to reiterate here, please do not scramble to write everything down, because I am going to be posting this video and the PowerPoint online. So I would rather you guys focus on listening and writing notes as needed, not just copying every single word down. All right, so here's another example of a number that is smaller, so it's less than 1. So we need to move the decimal, where we should move the decimal? To the right, and it's going to be like right after the 4, right? What do you guys think the exponential or the exponent's going to be? -4, right? So going through this real quick, when moving the decimal, try to avoid adding arbitrary zeros. That does matter. It basically talks about how accurate your value is. So only report the digits that are being shown there. Don't add your own digits. Okay, and since the decimal is moved to the right, we get 10 to the -4, meaning we have a small number, less than 1, negative exponent. All right, here are some examples. So notice how in the first number there, I did not add any extra zeros there. And we're going to go over significant figures today, but the way you report numbers is a little bit different depending on what your original number was. Another one I want to point out here is the third one, the 1.23. If you're asked to convert a number to scientific notation where the number is already, or the decimal is already in the correct spot, if you leave it that way, it's technically not in scientific notation. So both myself and the online homework will mark it incorrect if it's asking you to convert it to scientific notation. What you need to do is add the times 10 still, and then we put it to the 0th power, because 10 to the 0th is what? It's equal to 1. So you're basically saying 1.23 times 1 in this case. All right, before we move on here, do you guys need me to do any more examples with scientific notation, or are we okay? Okay. All right, so I'm going to go ahead and assume that you guys know this. If you're one of those students that are too shy to raise your hand and need more help, you're always welcome to come talk to me one-on-one during office hours, or talk to one of our tutors. All right, so the last thing, or the majority of the rest of the PowerPoint that I have here is about exponential rules. I do want to point out that this part is not in the textbook for some reason. I don't know why, but it's pretty important, I think. It's going to allow us to manipulate numbers a little bit easier. My goal for you guys is that when you work with metric and you're going back and forth in metric, you don't need a calculator. So I'm hoping, and then also when doing numbers that are all base 10, you should not need a calculator. And it's like when I'm at dinner or whatever, and I see people like pull, you have 10 people on there and they need to figure out how much the tip's going to be, and they pull out a calculator to divide by 10. It's kind of embarrassing, I think. People should be able to do that without a calculator. All right, so first things first, I already mentioned this one here. We have 10, anything raised to the 0th power is equal to 1. Here, if you have a case where you're multiplying numbers together that have 10 raised to some power, you just add them together. So I have this example down below where it says 10 squared times 10 cubed is equal to 10 to the 5. So I just added the 2 and the 3 together, got 5. But if you actually write out what you're actually doing, we have 10 times 10, and then times 10 times 10 times 10. That's equal to 10 to the 5. So it all works out. If you actually write it out, the rules should match. In the reverse case, if you're going to do a division, you subtract them. So 10 to the a over 10 to the b is equal to 10 to the a minus b. And same as the last example, I show you, I write it out here. 10 to the 3 divided by 10 to the 2 is just 10. And then if you write out all the digits here, everything cancels out, leaving you with 110 there. All right, next we have an inverse property. This is if you have a negative exponent. Basically, you can invert it. And in general, you can invert these signs anyway. So for example, if you had, say, 1 over 10 to the minus a, that's equal to 10 to the a. So if you do the reciprocal of it, you basically flip the sign on the exponent. There are times when we do calculations with doing these tricks will actually make things cancel out. And you won't actually have to punch them into your calculator, saving you time on the test. All right, this case here we have a unit raised to a power raised to a power. So 10 to the A raised to the B. In that case, all you do is multiply them. So A times B. And the example I gave here is 10 to the 3 raised to the second power. That's 10 to the 6. And basically, if you're squaring something, you're multiplying it by itself. So you're basically just doubling it here, 10 to the 6. All right, are there any questions about the exponential rules? All right. And we'll definitely see later in today's lecture, we are going to do some unit conversions, and that's when these little tricks will start to come up. I want to use them in application. All right, the next section here is all about significant figures. As you guys will learn as you go through chemistry as well as physics, these are going to be your bane, especially in the laboratory. In this particular class, I do grade on significant figures, but I actually only really mark off for it during the first set of material. If you guys go on to Chemistry 121, we will enforce these sig fig rules all semester long, and then again in 122, and then after that, again, OChem, we don't care anymore. So it's mostly in Gen Chem. And honestly, it mostly matters which lab you're in, how particular people are about them. Basically, what significant figures are is how we convey our numbers. And they're meant to be a representation of how accurate our instrumentation is. So keep in mind the focus that you've been using these numbers is the focus here is on the actual measuring of numbers, not just looking at numbers in a table. All right, but before we get into all that, I want to go over the difference between precision and accuracy. They actually are different. The word precision is referring to, like, if you're doing repeated measurements, how reproducible are those numbers? Like, are you getting the same number each time, or are they kind of going all over the place? Typically, if you're doing a procedure that has really poor precision, there's something wrong somewhere. So that means that either your method is bad, it could be that your instrumentation is bad, and then you also have the issue with the person doing the measuring is bad at measuring. Yes, that is a thing, and getting better, or getting more precise in your measurements is a skill that you'll learn in the lab. The next issue here is accuracy. It is how close the measurement is to the so-called true value. Oftentimes in science, we will have some values that have been well defined over the course of many years, and we consider those to be a true value. Sometimes people will consider an average of their data to be a true value. It all depends on the context of it. But here, the main thing is that accuracy is how close it is to the true value. I do have listed here the kind of calculations we're going to do. We are not going to do these calculations this semester. I'm just throwing them out there to let you guys know they are a thing in chemistry if you've seen it before in like a stats class or something. So we use standard deviation for calculating precision. Essentially what that does, it looks at how far the values are from each other. And then percent error is another thing we'll calculate next semester. And that's just how far off you are from what you should have got. All right, so here's a little analogy that's commonly used, little darts here about the difference between the two. So assuming that the bullseye is the so-called true value, something with good accuracy and good precision would be where all three darts are hitting the bullseye. Poor accuracy means, once again, that you're far from the true value, but in the second case, they're all really close. So that is precise but not accurate. And then the last one, kind of all over the place, the guy had too many beers or something, and it's neither accurate or precise. All right. And here's the chart about the metric system, but we're going to go ahead and switch over to the camera now. So, all right. Before that, are there any questions about what we just went over? All right, so I want to go over a little bit more with significant figures. And as I said, I did not get a chance to fully finish this PowerPoint here, so I'm going to go ahead and just use the camera. Hopefully it's not too much of a nightmare with the going in and out. And I apologize in advance because I will be changing this camera out today. There's actually a little thing I can do here too. That's going to make me stop recording. One sec. Remember, anytime if you guys have questions, you're always more than welcome to stop me and ask a question or ask me to clarify anything. Whatever you guys need help with, I'm here to help you. All right, and I'll move the thing out the screen here after I get something written on here. All right, that is in focus. And now it's going to turn off. Okay. All right, we usually call them sig figs for short. My goodness. Have an idea. Hang on, let me stop the recording here.